Hello, my name is Maximilian Klug and welcome to my presentation about the Cyber Physical Mobility Lab, an open source platform for networked and autonomous vehicles. The idea behind building the Cyber Physical Mobility Lab is to quickly see your ideas develop into reality and to somehow close the gap between testing and simulation and in real world. For this, we built a seamless testing platform that provides a simulation platform and platform for testing with model scale vehicles that can test the same code in both simulation and in model scale experiments. The Cyber Physical Mobility Lab consists of up to 20 model scale vehicles called mCars that drive on a map. A camera is mounted on the ceiling and records the driving area. A main computer is used to start and stop experiments and to provide a visualization of the lab. A router is used to connect the main computer to the mCars and the external computation units. These external computation units provide more computation power for the vehicles and are not mounted on the vehicles due to space and weight requirements. However, they are used in a logically one-to-one mapping, so one external computation unit is assigned to one vehicle. So the hardware of the mCar is based on an X-Ray M18 Pro chassis. So we used a common RC car chassis and built on top the sensors, an IMU and an odometer. And for actuators, we have a servo motor and an additional motor. And for computations, we use a Raspberry Pi for Wi-Fi connection, and we use it for clock synchronization of vehicles and sensor fusion and trajectory following control, and an ATmega microcontroller for reading sensor data and writing the actuators. So here we see the chassis with the battery, servo and motor placement. On top of this, we placed a printed circuit board that consists of the Raspberry Pi, the ATmega microcontroller, the IMU and the motor driver. And on top of this, on another layer, we built LEDs. That LEDs are used by the indoor positioning system we see later on the next slide. 3 of these LEDs are used for determine the position and orientation, and 1 is used to determine the ID of each vehicle. And then we have another board that provides the Hall effect sensors and magnets to measure the speed of the vehicle. So the indoor positioning system consists of a camera mounted on the ceiling with a top-down view on the field. The field is approximately 4 to 4.5 meters, and the vehicles drive on this field and are equipped with 4 LEDs, and the outer LEDs form a non-equilateral triangle to determine the pose, and 1 LED then flashes in a predefined frequency. The frequency is depending on the vehicle ID, so the positioning system can map the pose to the ID of the vehicle, so the external computation devices and the vehicles can use their the pose of the vehicles. The logical architecture of the Cyber Physical Mobility Lab looks as follows. We have divided the architecture in a sense plan act scheme and have additional infrastructure functionality in here. So the infrastructure provides the lab with a scenario server. So we have different scenarios with consists of the roads, the mission plan, simulation of passive traffic participants, and so on. And then the user can choose the scenario. Then the scenario data are stored in a map. The map consists of static information, dynamic information like moving vehicles, and preview information for planning in the future. And then the map changes based on sensors, so the positioning system or the vehicle sensors. They percept certain state of the vehicles, and these states or the data of the objects are then stored in the map to update the dynamic information. Then for the planning module or the planning modules, they can then use the map data, and additionally we have a module that adds an error or noise to this information to simulate errors that are common in real-world experiments, for example, inaccuracies of GNSS. Then we have a module for coordination, so that the vehicles coordinate with which vehicles they want to communicate. Then we have the decision making, consisting of routing planning and behavior planning, trajectory planning, and control. Then these plans or decisions are verified to ensure collision freeness, for example. And then the control inputs are written on the actuators so that the vehicles move, and then the sensors measure a different state and update the map, and so on. So the computational architecture then looks like follows. We have the vehicles and the computation device externally, and they share information. And this looks like this. We have so-called high-level controller that runs on the computation units, so not on the vehicle itself. And they this computation unit then performs, or the high-level controller performs in the tasks that are that require much computation resources. So the coordination, the decision making, and verification. And then they have resulting trajectories of the planning, and these trajectories are then communicated to the vehicles, to the mid-level controller. So the mid-level controller runs on the Raspberry Pi, implements a trajectory following controller. So the trajectory is then followed or translated into actual steering angles and accelerations. And it performs a sensor fusion. So the data of the sensors are then fused, and the estimated state is then communicated to the high-level controller. And we have the low-level controller on the 80 mega microcontroller. That is more or less a hardware abstraction. So it runs reads the sensors and writes the actuators and measure or transmit the measured data back to the mid-level controller. Then we have a middleware that is between the high-level controller and the vehicle, and this is used for ensuring a logical execution time. So we have synchronized computations on both the high-level controllers and the mid-level controllers, and this is for having experiments that can be reproduced and have a certain determinism that we can, we are not affected by undeterministic timing delays or something like this in our computation architecture. Then we have central and distributed computation possibilities in the CPM Lab. So for the central case, we have one high-level controller that plans the trajectories for all vehicles. Then it communicates over the middleware to each individual vehicle. And in the distributed case, we have one high-level controller for one vehicle. So we have as high-level controllers as we have vehicles on the map, and they still communicate over the same middleware. So the middleware is an important part in the CPM Lab to ensure determinism and reproducible experiments. For the communication in the CPM Lab, we use the data distribution service. The data distribution service is built with topics, publishers, and subscribers. So we have topics, for example, for the trajectories that are computed from the high-level controller, and the high-level controller then publishes the data into the topic, and the middleware subscribes this topic and then receives the data when the publisher publishes data on this topic. So then forwards the command to the vehicles, and it does the same with the state and the pose of the vehicles that are then forwarded to the high-level controller. Here we see the experimental concept. We see the low-level controller and the mid-level controller. They are the computations of these are performed frequently in a rather high frequency to compute control inputs and measure the state. And the high-level controller is triggered. So it only starts its computation when it's triggered from the middleware. And the computation time then may vary between different runs or different high-level controllers that compute simultaneously. So the middleware is used to get some determinism using a logical execution time approach. So the middleware takes care of the timing, so the high-level controller does not need to time or care about timing in its computation. So it can be best effort algorithms there, and it's easier to implement the high-level controllers using our middleware. Here we see a demonstration of the Cyber Physical Mobility Lab. We see the physical map on the right side and the visualization on the left side. In the visualization, the blue lines are the planned trajectories, and the purple line is the part of the trajectory that is currently used by the trajectory following controller, and the red lines are the driven path. The vehicles drive on randomly generated routes on the intersection scenario and avoid collisions by varying the speed. So they do this in a priority-based manner. So vehicles with lower priority will decrease their speed to avoid collisions with higher prioritized vehicles. To summarize, we transformed regular SC race cars to networked and autonomous vehicles. We built the CPM Lab infrastructure that contains a camera, a router, a main PC, and external computation units. We built an experimentation platform for large-scale network systems, and it is open source, so you can find information and updates on the construction and software on our website. And we are building a remote access, so you can not only download the software platform, but you can also upload your code, and it will then be tested on the physical lab with the hardware of the vehicles, and then we provide videos and data of the experiment. And it is used in teaching since 2019. Thank you for your attention, and for further questions, you can contact me via email.